Hello, in this video we will talk about the relationship between the pH and the pKa. In two previous videos I talked about pH fairly extensively and what is that. We'll also talk about pKa and what is that. Well, here we're going to see a relationship. So just to remind you, there are two different things. pH is a variable. It indicates how much H3O plus or hydronium ion there is in the solution. In other words, the concentration of H3O plus. And that can change all over the place. You can have lots of H3O plus or you can have very little H3O plus. So the pH changes as the materials that are in solution change. Again, it's a solution with some acid dissolved in it. pKa, on the other hand, is a constant and it indicates the strength of a particular acid. So acetic acid has a particular pKa, mandelic acid has a particular pKa, and so on. Every acid has its own pKa and you can look it up. So it's a constant for a particular acid. Now, as I said, these are not the same thing at all, but there is a relationship between them. Specifically, there's a relationship between the strength of an acid and the pH of a solution containing that acid. So listen to what I said. There's a relationship between the strength of a particular acid that might be in solution in water and the pH of that solution, which is variable, and it depends on the concentrations of all the different things in there. And be aware that you could have an acid in water, which by the way means that its conjugate base is also present, maybe not very much of it, but some, or maybe a lot of it, and not very much of the acid itself. But also you can have other things in the solution and it still holds true. So if you're talking about a particular acid in water, then there is a relationship between the pH of that solution and the strength of that acid. So here's the relationship. This is called the Henderson-Hasselbalch equation. It looks complicated, but it's actually a fairly simple equation. Notice that it has the pH in the equation. That's the pH of a particular solution. It has the pKa in the equation. That's a constant for a particular acid. And then it has the log of this ratio. And this is all one ratio, and the log is of that whole ratio. The ratio is the concentration of the conjugate base of an acid and the acid itself. There will always be both in any solution. If you put an acid into water, it will always form some of the conjugate base. Put the conjugate base into water, it will always form some of the conjugate acid. So these two will always be present in any water solution if either one of them is present. And the ratio of those two things is what this number is. If you take the log of that ratio and add it to the pKa, it'll give you the pH. That's the relationship. Now let's analyze the parts of this equation. Again, the pH is a number that we can measure on a solution. So there's a little picture of a solution. This is water. It's got some acid and its conjugate base dissolved in water, and again they'll always be both present in any water solution to some extent, and so we can measure the pH of the solution. That's a variable. It's a measurement that we can make on a particular solution. This is the pKa of a particular acid. So for example, here's a picture of acetic acid. It has a pKa of 4.75. That is a number that you can look up for acetic acid. And it may or may not be written on the label, but it could be. It's just a property of a particular acid, much like the melting point or boiling point would be. Notice the pH is not on the label because that's a variable. That depends on how much of it there is in water. And then, as I said, this that I put in a box here, that's a variable because you can have lots of the conjugate base and not very much of the conjugate acid, or not very much of the conjugate base and lots of the conjugate acid, or it could be 50-50. That ratio can be all over the place, again, depending upon what the pH is. So this is a variable, and it changes as the pH changes. So variable, constant, variable. And if this number, which is just a ratio, is a particular number, for example, it could be 0.25, or it could be 1.33, or it could be 2.7 times 10 minus 8, or it could be any number, huge, tiny, or somewhere in between. If that is a number, then the log of that is also a number. So for example, if the ratio is 0.25, then the log of that is the log of 0.25, which if you put it in your calculator, you will see is negative 0.6. Or if that ratio happens to be 1.33, then the log of 1.33, again, you can put it in your calculator, is 0.12. Notice, just out of curiosity, that if the ratio is less than 1, like for example 0.5, then the log will come out to be negative. If the ratio is bigger than 1, say 1.33, then the log of it will come out to be bigger than 0, in other words positive. And just to remind you about the way logs work, let's say this ratio comes out to be 10 to 1, or 10, then the log of that is 1, and the number in this box would turn out to be 1. So, for example, if we have acetic acid in water, so picture acetic acid dissolved in water in this flask right here. It could be there by itself. Well, of course, it has to have some of its conjugate base present as well. It's always true in any water solution. If you have an acid present, you also have to have its conjugate base present to some extent. Could be there without anything else, just water, or it could be other stuff in there as well. It could be HCl or sodium hydroxide or urine or saliva or any other stuff. But as long as there is some acetic acid in the water, there will be some of the conjugate base of acetic acid. If, for example, the ratio of those two turned out to be 0.25, as we said before, then the log of that is 0.60. According to the Henderson-Hasselbalch equation, you would take the pKa of acetic acid, which is 4.75, minus 0.60, because that's a negative number, and you would come up with a pH of 4.15. In other words, a little bit less than 4.75, more acidic than 4.75, so on the acid side. And that's because there is less of the conjugate base, more of the conjugate acid in that particular solution. But let's say in some different solution of this, there was a ratio of 1.33. The log of that is 0.12. You would add that to 4.75, and you would get a pH of 4.87. So again, the acid that's in here has a particular number, 4.75. But the pH changes depending upon what the ratio of the conjugate base to the conjugate acid is in that particular solution. Here's another interesting feature about the Henderson-Hasselbalch equation. If the concentration of the conjugate base and the concentration of the conjugate acid are equal to each other, in other words, it's a 50-50 mixture of the acid and its conjugate base, then that ratio turns out to be 1, as indicated here. The log of 1 is 0, and the pH then equals the pKa. That's an interesting thing. If you have a solution in which the pH is equal to the pKa, then you know that ratio is 1 and there's an equal amount of a conjugate acid in its conjugate base. Or, as I said, if the ratio is 1, those two are equal to each other and the pH is equal to the pK. But only at that point. pH doesn't always necessarily equal pKa, only under very specific circumstances. That is, if the ratio of the conjugate acid and the conjugate base in its solution is equal to 1. So, for example, if I just put some acetic acid into water, is the pH going to be 4.75? No, because the concentration of the conjugate acid and the conjugate base aren't necessarily equal to each other just by adding acetic acid into water. In fact, there'll be far more of the acid than of the base, so this would be a number that's way less than 1. So this would be a negative number, and you would subtract some from the pKa, and you would get a pH that is much smaller than pKa, in other words, more acidic than 4.75. It's going to turn out to be about 2, I think, is the actual number. Okay, now just out of curiosity, let me explain where the Henderson-Hasselbalch equation comes from. It's actually, as I said, a fairly simple derivation. Now, this looks complicated, but it's really not too bad. So what is this formula that we have right here? This is the definition of Ka. Remember, Ka is always concentration of H3O plus times the concentration of the conjugate base over the concentration of the conjugate acid. That's just the definition of Ka. That is going to be equal to concentration of H3O plus times this ratio. So this step right here is just essentially separating out the conjugate base and conjugate acid into one factor and the concentration of H3O plus into a different factor. So these two things times each other. Then let's take the log of both sides. So if we take the log of Ka, in other words, the log of this product, it's going to be equal to the log of H3O plus the log of this ratio. So you might say, but this was a multiply here, and all of a sudden it became a plus. Well, that's because a log is an exponent, and what happens when you multiply two things with different exponents? You add the exponents. So that's why this is a plus now. It's just the way logs work. Then let's take the negative of both sides. So log of Ka becomes negative log of Ka. Log of H3O plus becomes negative log of H3O plus. And instead of a plus sign for the log of the ratio, we now have a minus sign for the log of the ratio. So all I did was just negativize the whole equation, if you will. But now notice that what is the negative log of the Ka? That's just the pKa. What is the negative log of H3O plus? That's just the pH. So this equation becomes pK equals pH minus the log of the ratio. Now let's just add the log of the ratio to both sides and switch it around. You get pH equals the pK plus the log of the ratio. There is the Henderson-Hasselbalch equation. So you can see in just a couple simple steps we went from the definition of Ka to the Henderson-Hasselbalch equation. So really, the Henderson-Hasselbalch equation is just another way of saying this familiar equation, which is the definition of the Ka of any acid. So there's your relationship between pH and pK. Thank you for your attention.